So I mentioned that on exams, definition statements, theorem statements can be on the exams. Calculations as well. Though no calculators will be allowed, I'll make it so that you can do the calculations without a calculator. Modular arithmetic, for example. And subproofs. Proofs of similar difficulty to proofs that we've talked about with uniqueness of identities and inverses and those properties that I was writing on the board there are certainly possibilities. Here's another possibility, and this is worth bringing up as an example in its own right as well, to re-emphasize the idea of an equivalence relation in partitions. Here's another example of an equivalence relation. It's called conjugacy of group elements. Let G be a group and let A and B be elements of G. We say that A is conjugate to B if something happens. If this happens, if there is an X in G such that XA, X inverse equals B, then we say A is conjugate to B. And we could write, if we like, this kind of thing when A is conjugate to B. And if that is a definition of this symbol, that there exists an X in G so that this is true, then this does define an equivalence relation. We can verify that it's an equivalence relation. I won't write it as a proof, but I'll write some equations that will help you believe it. First of all, the fact that E inverse equals EAE equals AE equals A implies that A is conjugate to itself. I will say the word conjugate. If A is conjugate to B, so there's an X, so that this is true, is B conjugate to A? Is the symmetric property holding here? It does. To see why, left multiply both sides of this equation by X inverse, and right multiply both sides of the equation by X. This simplifies down to A. I won't show the steps. You can use the associative properties to show those steps. And you can also, well, if you like, you can put this thing on the left side and the A on the right. And I'm also going to write this. Because the inverse of X inverse is X. That equation says both that this symbol is the inverse of X as a group element, and it also says that the other one, the X, is the inverse of X inverse. So you can always replace any group element like this X here, this one here, with the inverse of the inverse. And now this is in the form of something times B in this case, times the inverse of the something equaling A in this case. So therefore, A being congruent to B implies B is congruent to A. The symmetric property holds. Finally, the transitive property. If A is congruent to B and B is congruent to C, then there exists group elements X and Y such that X, AX inverse equals B, and Y, B, Y inverse equals C. Can I combine these equations to say A is congruent to C? Does the transitive property hold? Yeah, essentially, let's see here, you could take this equation B equals this and substitute it into there in place of that B. That will imply y times XA X inverse times y inverse equals C. I need the associative property, and I also need the sock-shoes property to finish this. Write this as YXA X inverse Y inverse in parentheses equals C, but now by the sock-shoes property, you could write that like this. And that will imply that A is congruent to C. If you add sentences of brief explanations, then this can become a proof. That could be of the level of a proof on the first exam. Mention the properties you're using, mention the associative property, mention the sock-shoes property. Right, and this is fitting this definition as well. That should be noted, though you probably don't need to write that down. That does imply A is congruent to C. This is an equivalence relation, and therefore it also partitions the group. Any group, this can be defined for any group. Though for an abelian group, it's trivial in a sense. Everything is only congruent to itself for an abelian group, because you can move the X and X inverse around to say that if A is congruent to B, then A in fact must equal B. So it's a trivial kind of equivalence relation for abelian groups. It's only more significant than for non-abelian groups. It is actually a pretty important kind of equivalence relation. Since we're using the word conjugate, the equivalence classes are called conjugacy classes. And I should also remind you from linear algebra, which I think is always a good thing to do, remind you of things from linear algebra, that a group of square matrices under matrix multiplication, for example, the kind of group we talked about where the determinant was non-zero, the general linear group, conjugacy has actually got a different name. It's called similarity. And the equivalence classes are called similarity classes rather than conjugacy classes. We've got a bunch of different names for the same concept here. And it's a pretty important idea in linear algebra. Similar matrices share many properties. They have, for example, the same determinant. They have the same eigenvalues. And their powers, two similar matrices, if you raise them to, say, the 10th power, those resulting matrices will also be similar. That actually ends up being a useful thing if you look back in your linear algebra book when they talk about change of basis. These facts about similarity really are coming into play with change of basis, change of coordinates, and it's a good problem-solving tool, actually. You'll see that if you look through your linear algebra book. Let's do a brief review of Cayley tables and remind you of a concept. Then we're going to go on to a few more new things here. We did the Cayley table for what was it, Z4 and Z5 by hand. Here's the Cayley table for Z6. And again, if you put the group elements in the same order along the left as you do along the top, the inner matrix, being symmetric in this case, is illustrating the fact that this is an abelian group. For example, 3 plus 2 equaling 5 mod 6 is the same as 2 plus 3 equaling 5. It's symmetric across the main diagonal, like usual for symmetric matrices. We can also quickly see, if we put the group elements in the same order along the left and the top, that if you look along the main diagonal here, that only 0 and 3 are their own inverses. The other ones are not their own inverses. That's another property worth noting. We can compare this, for example, with the Cayley table for D3, the group of symmetries in an equilateral triangle. And always remember, D3's got 6 elements. D4 has 8 elements. D5 has 10 elements. You always double the subscript. The 3 refers to the fact that these are symmetries of an equilateral triangle with 3 sides. D4 is symmetries of a square that's got 4 sides. D5 is symmetries of a regular pentagon that's got 5 sides. But you have both rotations and reflections, and so you have to double the number of elements. Again, I put the group elements in the same order on the left as on the top there. We can see here that this group is not abelian, for example. R240 composed with V, meaning really work from right to left. V is done first. First do the vertical flip, then rotate by 240 degrees. Gives you D prime, the rotate of the flip across that line, the off diagonal, so to speak, for the triangle. The other way around, V R240 is not D prime, it's D. Look at this matrix across this diagonal. These are not equal, it's not a symmetric matrix. This group is not commuted, not abelian. We can also, again, quickly see which elements are their own inverses by looking at the main diagonal. R0 is its own inverse, it's the identity element. The flips are their own inverses too, which makes sense. Do a flip twice, you get back to where you started. R0, R0, R0. You also see some other interesting structure here. This matrix, this 6 by 6 matrix of the products here, compositions, is kind of like a block matrix. The rotations occur up here and down there, and the flips occur over here and over here. In this particular kind of example, that's just illustrating composing 2 rotations gives you a rotation. Composing 2 flips gives you a rotation, 2 reflections. And composing a rotation with a flip with a reflection gives you a reflection. That kind of structure is something worth observing too. And it will come up in some pretty significant ways about chapter 8 or so, chapter 9. Here's food for thought. We might be able to use these tables to decide whether these groups are isomorphic or not. Are they the same group essentially or not? Well, I hope you pretty much quickly realize, no, they're not the same, even though they have the same number of elements. For one thing, this one's abelian, whereas this one's not. For another thing, this one has 2 elements that are their own inverses, whereas this one has 4 elements that are their own inverses. So even though these groups have the same number of elements, the structure of the group is different. They are not isomorphic. Isomorphic means same form. Focusing not on the meaning of the symbols as numbers or functions, but on the structure of the table. Do the tables have the same structure? No, they don't. Sometimes it might not be clear whether they have the same structure or not, because maybe you put the elements in the wrong orders to compare them correctly. And maybe if you reorder the elements along the left and the top, keeping the order the same on the left and top, ordering them when you compare, maybe then the isomorphism will be more apparent if there is one. So you got to be careful in thinking about it that way. All right, here's some more new things for today. Again, this is a very abstract day, you might say. We will do more examples next Monday of this stuff. New definitions, theorems, and examples now from chapter 3. The title of chapter 3 is Finite Groups and Subgroups. These definitions are going to be really important too. First of all, what is the order of a group? And can it be finite or infinite, or both? Let G be a group. Loosely speaking, you could say the number of elements of G is the order of G. Or I'll say it this way, the order of G is the number of elements, I'll put number of elements in quotes, in G. Certainly if G has finitely many elements, it makes sense to say that. If a group has 10 elements, its order is 10. If a group has a trillion elements, its order is a trillion. But G could have infinitely many elements. The group of integers under addition has infinitely many elements. The group of rational numbers, the group of real numbers, the group of complex numbers. GL2R has infinitely many elements, right? Because the entries of the matrices can be any real number. If I do something like this, that doesn't have infinitely many elements. Maybe we should quickly figure out the order of this group. GL2Z2. It's trickier than you might think. You might think since we're talking about 2 by 2 matrices, and since Z2 has 2 elements in it, 0 and 1, you've got 2 choices for each entry. So you should have 2 times 2 times 2 times 2, 16 elements. But that's not quite right because you forgot about the fact, if you think that way, that the determinant has to be non-zero. So that reduces the number of elements. I'll leave it for you to figure out that I believe GLZ2 has 6 elements, actually. There's only 6 of those matrices whose entries are either 0 or 1 with a non-zero determinant. One of which is the identity matrix. 1, 0, 0, 1. This, I believe, is a 6-element group. The order of the group is denoted by that. It's tempting to say the absolute value of G, but don't. Say the order of G. So again, if G has finitely many elements, then the order is the number of elements. What if G has infinitely many elements? Then you could just say it's infinite order. And you could write, if G is infinite, I won't mark it wrong if you write that the order of G equals infinity. I will not mark that as wrong because we'll take that as a valid shorthand. Infinity is not a number for us. Actually, infinity can be a number in some math classes, but not in this one. Not in most undergraduate math classes. But this is notation to emphasize G has infinitely many elements, not finite. A little more officially, you can say the order of a group is its cardinality as a set. If you've ever heard the word cardinality. And there's more than one kind of infinite cardinal number. There are actually different kinds of infinity. If you've never heard that before, that sounds really, really strange, but it's actually true. You can also talk about the order of an element of a group. And is it finite or infinite? Well, let's use a little g for the group element this time. The order of g, little g, the element, denoted, again, don't say absolute value of g, say order of g. Is defined by, well, let's go ahead and write it as a piecewise formula. The order of g is a positive integer n if n is the smallest positive integer satisfying the equation g to the n equals the identity. And the order of the group element is infinity if there is no such n. Well, I should probably say if there is no n greater than 0 such that g to the n equals e. Or I could say g to the n is not equal to e for all n greater than 0. We are talking about integers here for n. Can't define fractional powers of group elements in general. G to the 1/2 in general, you cannot make sense of that. If there is no positive n, so that's true. Let's go back to the Cayley table quick. So the order of Z6 and the order of D3, both of them have order 6. How about orders of elements? What's the order of the identity element? 1, actually. The order of E is 1 because 1 is the smallest positive integer making this equation true. The order of the identity in any group is 1. Any elements of order 2 in Z6? You got to think additively now, not multiplicatively. Anything added to itself give the identity? Yeah, 3. 3 has order 2. 3 plus 3 is 0, the identity. What's the order of 1? Think additively. 1 plus 1 is 2, not 0. 1 plus 1 plus 1 is 3, not 0. 1 plus 1 plus 1 plus 1. Did I say 4 ones there? Is 4, not 0. It's only until you get to 1 plus 1 plus 1 plus 1 plus 1 plus 1. 6 ones that you get back to 0. The order of 1 is 6. And we write an equation like this, which looks really weird, doesn't it? Add in Z6. The order of 2. 2 plus 2 is 4, not 0. 2 plus 2 plus 2 is 0. The order of 2 is 3 in Z6. Any elements of order 4? I claim there are no elements of order 4 or 5, though that would take some checking. Down here, the order of the flips is 2. The order of each non-identity rotation is 3. Right? Think about that. R120 composed with R120 composed with R120 is R0. 3 compositions of R1. You need to compose R120, raise it to the 3rd power is the way I should say it, to get back to R0. I can see I'm not going to get to the modular arithmetic that I was hoping to get to today. I will do that first thing on Monday, the modular arithmetic, which is again related to that number 7 that you did in the assignment that I didn't grade because there were some subtleties with it. And I was low on time. Let's end class today by talking briefly about the idea of a subgroup. G be a group, and let H, say, be a subset of G, if H is in fact a group under the same operation as in G, that's very important. Then H is called a subgroup of G. And we denote it in a special way. Like that. Do not say less than or equal to. Say H is a subgroup of G. Here H is a subset. All the elements of H are elements of G. If that set is also a group under the same operation, we call it a subgroup. We write this, do not say less than or equal to. It could equal G. H could be equal to G. If it's not equal to G, then it's called a proper subgroup. If it does equal G itself, then it's not a proper subgroup, it's a non-proper subgroup. Also, it's the case that in any group, the set consisting of just the identity element is always a subgroup. It's called a trivial subgroup. You're going to see in the reading, if you haven't already, that there are a bunch of subgroup tests. Think of these tests for whether a certain set is a subgroup or not as analogous to the subspace test that you did in linear algebra. Talking vector spaces and subspaces. These tests are, if you look back in your linear algebra book, you'll see these tests, at least one of them is pretty similar to what you did with subspaces in linear algebra. All right, see you on Monday.